Welcome to Serverless Architectural Patterns and Best Practices. My name is Sascha Möllering, and I'm an AWS Solutions Architect based in Berlin. So our agenda today is to focus on three different serverless patterns. So first, we will start with a brief introduction into microservices and serverless foundations. And this is important for the understanding of the patterns we will discuss today. So first of all, we will start with the web application pattern, which is also applicable to mobile backends, microservices, and API deployments. And then I'll talk about the data lake pattern, because a lot of customers want to start building data lakes, and I want to share a few best practices and implementations. Specifically, I want to talk about sub-patterns related to analytical processing. And last but not least, I'll talk about stream processing. So before we will dive into the patterns, we will take a closer look at some of the foundational concepts of serverless applications. So let's start off with the concept of microservices and what this term actually means in the context of serverless architecture and which paradigms are important. So this is not your usual microservices introduction, but it's really tailored to serverless approaches. So I can imagine that many of you have already seen something like this, so I will only go briefly over those different topics. So with microservices architectures, you can have different languages and platforms for different microservices. So let's say you do rapid development and test things out and use, for instance, Python for that. And for other workloads, for very I/O-intense microservices, you want to use languages and platforms like Golang. So and this is possible in a microservices architecture. And also, microservices focus on one specific functionality in one specific domain. And the team that builds the service is responsible for the production. And microservices offer a simple interface and hide implementation details. So this also reflects or goes with the polyglot nature of microservices. And also microservices can be deployed independently from each other. So this is a very, very important approach. And there is no central service. Services talk to each other. So microservices in general should be stateless, and if you have state, it should be kept in external systems. So let's assume you have a system where you have like session information, and session information can be stored in systems like, let's say, Redis or Memcache. And data, of course, should be stored in relational databases or NoSQL systems, depending on your specific requirements and implementation details. And loose coupling should be implemented using, for instance, REST interfaces or queues if you want to have asynchronous communication between microservices. So a lot of customers use, for instance, SQS, Kinesis, Kafka, or other queuing mechanisms for the implementation of asynchronous communication between microservices. So extracting common code to a library seems to be developers' best practice, and because it the reuse boosts the development, right? No, actually this is wrong, because shared libraries or shared SDKs should be avoided because it has a negative impact on the release process. So, and by shared libraries, I have issues with my, okay. And by shared libraries, I mean libraries that create coupling and dependencies. So don't use shared libraries for business logic and models. So instead, accept redundancy, introduce a shared service, or reslice your microservices. And keep in mind, duplication is far cheaper than the wrong abstraction. And please don't make any assumptions about IP addresses or directories. And this is really important because this can have a huge impact if you start migrating your services. So one example, in your own data center, you have applications that rely on certain hard-coded IP addresses, for instance, and in file system layouts. And if you start migrating those applications to AWS, you will run into issues because, for example, you don't have this specific IP address anymore. And if you have a lot of microservices communicating with each other, so for instance, if you use Docker-based microservices with ECS or Kubernetes, you should always have a mechanism and services for registration. So popular examples for that are, for instance, Consul, etcd, Eureka, or Zookeeper. And it is always a good idea to use lightweight protocols for communication. So HTTP and REST for synchronous communication, for instance. And for asynchronous communication, you can use messaging implementations, as already mentioned, Kinesis, SQS, RabbitMQ, or Apache Kafka. So we took a closer look at the microservices and some of the best practices. And in the next few minutes, I want to cover a few of the foundational concepts of serverless applications which are applicable to all patterns we're discussing today. So all of these patterns are very well adopted and also used by AWS customers today. So let's start off with what a serverless application actually is. So as you all know, on AWS, there are many, many choices to deploy your applications. So certainly you can deploy them in virtual machines, like EC2 instances, and you can deploy them into Docker containers if you want to, on EC2 instances with services like ECS and EKS. And there is this case of services that's kind of in the middle, which is called managed services. And these services where you may not really be responsible for the service, but servers still exist. So servers are still important when you consume that particular service because you need to be able to right-size that service and potentially scale that service, and you define that by defining the number of servers and the instance type of the EC2 instances. And on the right, you see the class of services we will be focusing on today, which are serverless services where servers are not present at all in the consumption of those services. So, and this is really important, you are reducing your operational overhead. And there are 4 common tenets of serverless applications. Again, no servers to provision or manage, but also you never pay for idle with serverless applications. So for example, if your application is cyclical in nature, so maybe you do a lot of in-the-month processing, you don't pay for these times when it's not in use. And also, serverless applications have built-in high availability and disaster recovery. So all of the serverless services we talk about today sit on a regional level on an AWS. So they automatically span over all availability zones and provide you that built-in high availability and disaster recovery. And perhaps the most important aspect of serverless applications is it scales with the usage. So as user requests that are coming in start growing, the serverless application will scale as well. So this means not servers are the unit of scale, but Lambda functions. And we already talked about the general concepts of stateless architecture, but what does being stateless mean in the context of AWS Lambda? So a state like user sessions, as already mentioned, should be stored in services like DynamoDB or S3 or Elasticache. And Lambda functions execute in a container. So it's a sandbox that isolates them from other functions and provides the resources such as memory specified in the function's configuration. And this container exists for a certain amount of time. Please don't assume any affinity with the underlying compute infrastructure, because files that are stored in /temp in your Lambda function may be gone in the next call of your Lambda function. And it's really important to speak about how Lambda functions behave. So when you first invoke a Lambda function, it goes through a process that we call a cold start process. And I'm sure that many of you have heard that already. And this involves downloading the code to Lambda, starting it up in a container on a Lambda host, and then running additional initialization code that you have defined in the actual implementation code of your Lambda function. So you can see in this example, on the right that I'm importing some external libraries and making a connection to a RDS database. And what is important here is that I'm doing that outside of the handler. That happens only during the cold start process. So Lambda will keep the container available for a period of time so that if subsequent calls or invocations will hit this Lambda function, it will be warm. And it's really important to take advantage of container reuse as much as you can in your serverless application. Because it makes them more performant. So each subsequent invocation will then just happen on the handler level, which you can see here highlighted. So if cold start times are an issue for your application, you can always keep them warm by scheduling them in with CloudWatch events. And also keep in mind you can attach an ENI, so an elastic network interface, which is like a virtual network card, to your Lambda functions to allow them to communicate with private resources inside of your VPC. So one very popular example here is, let's say you want to set up a Redis cache, and you want to set up this Redis cache in the private subnets of your VPC. Then you have to attach an elastic network interface to your Lambda function and to have the ability to communicate with this particular Redis cache. But this should be only used if needed, because it will actually add to the cold start time. A few other Lambda best practices. So you definitively want to minimize the package size to only include necessities. And this is really important if you write your Lambda functions in Java, for instance. So some AWS SDKs like Java, for instance, are kind of modular. So this means you bring just the components you need. For example, modules for DynamoDB or modules for Kinesis. And it is always best practice to separate the Lambda handler from the core logic of your function, because this dramatically improves the testability of your code. So you can write your unit tests for your business logic, test it, and have a separate layer of invocation code that is calling your business logic. And also, please leverage environment variables as much as possible, because this is an amazing way to change how your code behaves without directly changing your code. And a lot of customers use this concept to use the same Lambda function in different stages of their environment. So for instance, you can have one Lambda package that runs in your test environment, in your integration environment, and in your production environment. And depending on the environment variable, the Lambda function downloads a set of configuration and uses particular sets of your infrastructure. And it is always recommended to self-contain dependencies in your package as much as possible. So keep in mind that Lambda has a single configuration option to change the memory allocation of your Lambda function. And by changing this configuration, you can also change the amount of CPU that is associated with this particular Lambda function. And remember, there is a CloudWatch metric called max memory used, which you can use to fine-tune your Lambda configuration. Another great way to get insights into your Lambda function is to leverage AWS Xray. And it is very easy to integrate, and there is a tight integration into AWS Lambda. So it's just a checkbox to enable active tracing, and this gives you immediate information how your Lambda function in the context of the Lambda service is performing. So Xray will also give you a delay map for service interactions. So you can see this is delay map over here. And there's also a way to customize the sampling rate of Xray. So, and here's a small sample to show you how to do this. So the second line of the code sample is including a sampling configuration file to configure a custom sampling interval. And in the third line, you see that we actually wrap the require statement for the AWS SDK in order to instrument AWS SDK. So in case this is S3. And here's a quick example of what's produced in Xray for a Lambda function. So the top half of this picture shows the Lambda service itself, and you can see dwell time as an example, or how long a function waited for the Lambda service to be executed. And you can see the entire duration of the Lambda function executing from start to finish as well. I also want to talk a little bit about deployment and modeling of your serverless application. I'm not sure how many of you have already used AWS SAM. Okay, just a bunch of people. So AWS SAM is built on top of CloudFormation. So, and this is actually good news because you can reuse any tool that supports CloudFormation. And SAM also supports many CloudFormation features, like, for instance, parameters or intrinsic functions. And you can combine SAM resources with CloudFormation resources. SAM also includes some ways to deploy your application. So it will provide a unique artifact for deployment, load that into an S3 bucket, and then it will leverage CloudFormation change sets. You also may have heard AWS has published the open source project SAM Local. And actually this project is really, really exciting because it provides you with an effective way to do local testing of your Lambda functions before you deploy them into the service. So what you can do is you can develop, you can test mock events, test your Lambda functions, and it even gives you a local copy of API Gateway, which you can spin up. And this local copy of API Gateway supports hot reloading, so you can change your code on the fly. Once you have finished your local tests, SAM Local has a CLI that includes all of the SAM commands to package and deploy your application to the Lambda service. And probably the best way in AWS to deploy CloudFormation templates in a custom pipeline is to use CodePipeline, which is a continuous integration service. And it has built-in support for AWS SAM and CloudFormation templates. And you can also integrate additional stages in your pipeline, for example, build stages to do builds and potentially testing stages as well. So, and you can leverage CodePipeline to deploy to different stages. So, for example, if you want to do some testing in a development environment, and if tests pass automatically, deploy into your staging environment, potentially have a manual approval step before it goes into production. And I also want to mention a relatively new capability within Lambda that provides the ability to have a Lambda alias mapped to multiple Lambda function versions. So this is very important for canary deployments that you can do now with Lambda. So now you can define in your SAM template multiple function versions and specify an amount of traffic and an interval in which traffic will move over from one version to another for your canary-based deployments. And this is also fully supported by CodeDeploy. And CodeDeploy will actually monitor CloudWatch alerts for failures in your newer Lambda function versions. And if failures occur, it will also initiate a rollback for you. So let's go ahead and start talking about the first pattern, which is the web application pattern. So this is a very common pattern where we have static content in the upper part of the architecture, maybe some resources in S3 that are delivered through the content delivery network, Amazon CloudFront. And at the bottom, you might have the more dynamic calls and content going through API Gateway APIs. And those APIs are backed by Lambda functions potentially, but they could also be backed up by other services, like let's say you run your business logic and your application in a Docker container. So this is also possible. And in addition, you have other downstream services, like in this case DynamoDB. And it's really important not to leave out Cognito in this pattern, because Cognito is what can provide sign up and sign in your application, as well as identity federation. So this pattern is well used and well adopted across a lot of different websites today. Security is also worth discussing in a serverless environment and for serverless applications, because it's a little bit different from security for traditional applications. So each of these services we've talked about in this pattern has also a lot of security features. I won't be able to go over all of them, but I will just call out a few. There is a so-called origin access identity capability with CloudFront to ensure that only CloudFront can access the resources that are stored in your S3 bucket. So both CloudFront and API Gateway now support AWS Certificate Manager TLS certificates. And then, of course, IAM is heavily leveraged to make sure that API Gateway has privileges to call Lambda functions. One of the most important topics when we talk about security is authorization of your API Gateway methods. And there are many different ways to do that with API Gateway, and probably the most common is IAM authorization. And there are a few different ways to leverage Cognito and provide those IAM credentials. So in addition to IAM, there's also a custom authorization capability within API Gateway. Also, a few months ago, AWS had a really big announcement around regional endpoints with API Gateway. And this is about decoupling API Gateway from CloudFront. And this is actually a pretty big release because it enables multi-region serverless applications. And with this pattern, you can actually create regional endpoints for API Gateway. And as you can see here, separate regions. And each of these can be associated with the same custom domain name. And then you can use weighted routing, for example, with CNAME to direct traffic from a request to the same name to different regions using, for example, weighted routing policies. And then lastly, I just want to mention a few frameworks that are available to help you adopt serverless web applications. So the first for Python developers in the audience that are familiar with the decorator-based APIs is Chalice. And Chalice allows you to model APIs and API paths with Lambda functions and deploy applications from Python code into serverless environment. So if you have Node.js Express applications or Java applications, there are additional libraries and frameworks inside of GitHub to convert those over to the AWS serverless platform. Now let's talk about pattern 2, the serverless data lake pattern. So one thing that's for sure when you think about data analytics and processing data is that your needs and requirements are most probably going to change in the future. So they don't usually stay consistent. And that's the reason why adopting a data lake is so important, because it sets the foundational layer and the foundational components for you to be more agile. So one of the most common tenets of a data lake is that you get all the data of your organization into that data lake. And you may not know exactly what you're going to do with the data right now, but maybe in the future you've changing requirements. So the data lake should implement a schema on read strategy so that as you request the data, you can specify the schema to do so. So in the future, when new questions arise, you'll be able to do that with the schema on read approach. And the data lake should be a home for all of your data, whether it's structured, semi-structured, or totally unstructured data. And it should also support BI and analytical use cases as well as machine learning. And last but not least, a data lake should implement decoupled compute and storage. And here's a look at the serverless data lake architecture at the center. The architecture is S3, which has a lot of great features. And obviously, a data lake needs to be able to accept data in from a lot of different forms. So it's very important to ingest data from a lot of sources in great volumes. Cataloging and searching is also a very important aspect of a data lake, so we'll cover a few of these patterns that include DynamoDB and Elasticsearch. And this is basically all about discovering your data. And then at its core, analytics and processing is very important, obviously, to a data lake. There are many different serverless services that you can use to do analytics and processing, like, for instance, Athena and Lambda. There are also services that aren't serverless that have a very important role here, like, for instance, EMR. And there's certainly a security component to a data lake. So you want to be able to manage access to data to different users or groups, and you want to be able to encrypt your data. And AWS has many different ways to do that. So auditing access to your data is also a very important aspect, which can be implemented using CloudTrail. And then lastly, you need a user interface for your data lake. So you need a way for your users to maybe log into a portal and begin to discover and search the information in your data lake. So let's talk a little bit about S3 as foundation for the data lake. So you have a virtually unlimited amount of storage in S3 and basically no aggregate throughput limit. So multiple storage classes are available to store your data in a cost-efficient way, and also versioning and encryption is fully supported. So now let's talk specifically about cataloging and searching. So there's a couple of patterns here to showcase. So the first pattern is more of an event-based pattern. So as data arrives in S3, regardless of how it arrives there, I run a Lambda function to store metadata in DynamoDB. And that could be maybe information about the data set. And then I have an update stream of the data written in DynamoDB, and a Lambda function that reacts on that and sends this information to Elasticsearch for searchability to build a searchable index. And I've included a link here to a whole Answers article doing exactly this. Also, AWS Glue plays a very vital role in this space. So Glue can dispatch crawlers either on a scheduled basis or on demand. And Glue can automatically look into your files and infer the schema around those files and build a catalog from that information. And that data catalog that Glue builds automatically with these crawlers is also Hive Metastore compliant. So it can have immediately define tables and define to query then in a BI tool of your choice, like, for instance, QuickSight. And from an analytics and processing perspective related to the data lake, there are a lot of tools out there to provide access to S3 and to do your analytical and processing workloads. But I want to focus here on Athena and AWS Lambda for the different sub-patterns. First of all, Athena. So what is Athena? It's a serverless interactive query service, and it provides you a way to submit SQL queries to the data that you have stored in S3. And what's really amazing about Athena is it is super fast. So in this example, we process 170 gigs of data in under 45 seconds executing this query. And you also see the group by and order statement. So this is almost 4 gigabytes per second, and it uses Presto as the engine for data manipulation. And there are some efficiencies and best practices around Athena. So I've got a link here to include the top 10 of those, and I just want to pick a few of them that are fairly important. So first of all, you can leverage Athena to partition your data. And Athena's pricing model is based on the amount of data that you scan. So if you can reduce the amount of data that you scan, you can save money, and you can do this very efficiently by partitioning your data. So if your data is stored in a 3 bucket in a path that you see here, Athena will automatically partition your data, but you can, of course, specify manual partitioning schemes as well. And I strongly recommend columnar data formats for the data that is stored in your data lake. So, for instance, Parquet, Avro, or ORC. And also, please optimize file sizes, and because this becomes very, very important. So if you have a lot of small files, you will have a lot of overhead interacting with S3. But if you have just one file, it may not give you the parallelism your compute environment needs. So in this case, splittable compression can help here. There's also a serverless batch processing pattern that I want to show you, which can be used for your analytical processing needs. And this is more of a do-it-yourself approach, where you have a Lambda function that takes your source data and splits it up, maybe by lines or by size, and hands it off to a set of mapper functions that process your data and write results to Amazon DynamoDB. And then we have a reducer function collecting that data and storing the end result in S3. So it's like a MapReduce implementation without servers. So imagine you're responsible for building and operating a highly successful e-commerce website. So you had a great Cyber Monday. You've been collecting click-stream data for all of your actions that were happening on your website, but you're processing them on a daily basis. So this means 24 hours after this event. And your management gives you the challenge to bring down that time from a day to just a few minutes. And this is basically a classical example of having to deal with a lot of streaming data that is coming in. And this is a stream processing application. So as we look at the characteristics, which are shared by many different applications, you have things like high ingest rates, and you want to do near real-time processing. And you may also have spiky traffic. So once you get a message in, you want this message to be stored durable. So message durability is very important here. And in many cases also the order of messages flowing in is also important. So let's take a look at an example of how a typical stream data ingestion architecture could look like. So the core of this architecture here is Amazon Kinesis Firehose in the middle. So Kinesis Firehose is a service that lets you ingest large amounts of data, buffer them in micro batches, and delivers them to destination services. So this lets you essentially decouple a high rate of messages flowing in your system from services that can better deal with batches of data. So you can send data in raw record form directly to the Kinesis Firehose API, or you can install a Kinesis agent, which will look at your log files, and as new messages come into the log files, it will post this data to the Kinesis Firehose delivery stream. And if a record is in a delivery stream, you can also do transformations on those records. And this is really interesting. So you can invoke a Lambda function, as you see here. You can invoke this particular Lambda function with the raw record and have custom logic. So once the transformation is done, those records are sent back to Kinesis Firehose, and Firehose now makes microbatches and delivers them to destination services. So for your ETL requirements, you can write a Lambda function, transform the data that is flowing into your Kinesis Firehose stream, transform the data and send it back to the stream. And as you implement this pattern, some best practices. Firehose basically has two different parameters you need to tune. So the first one is the buffer size, and the other one is the interval. So these two parameters interact together to define how frequently messages are delivered to the destination service and how big each of these batch records are. So Firehose also lets you enable compression, which is also a great way to reduce your storage costs as well as your data transfer costs. So one additional useful pattern is the so-called source record backup, which delivers a copy of the raw data to a S3 bucket of your choice. This is very useful if you run into issues when the transformation has issues, so you can go back and take a look at the raw data that is flowing into your system and see what actually caused this particular issue. And specifically, if you are loading data into Redshift, it is a good idea to take a closer look at the blog post under this link here, which shows some of the best practices how to load data into Amazon Redshift. Let's take a look at an example of a real-time application. So imagine we have a large fleet of IoT sensors sending things like temperature data. And we want to smooth out the noisy data over a 60-second period and compare that to a threshold that we have defined in a DynamoDB database. And this is basically a pipeline that can achieve that. And starting from the left, we have data that arrives from the Kinesis stream. And we attach that to a Kinesis Analytics application. And Kinesis Analytics is a service that lets you perform near real-time analytics to data coming through a stream. And you represent this logic as SQL statements. And the parts in white basically set up the source as well as the destination definitions. And the parts in orange set up that 1 minute window in which we want to average our data. And the parts in blue represent the aggregation. So we calculate the sum of the measurements the sensor sent us, and we will also count the number of measurements. So this gives us the capability to calculate an average, and then we're grouping that whole measurement set by the device ID. And you can see it is actually quite simple to implement a complex processing requirement just using a SQL statement. And once we have those aggregated measurements, we can deliver those to a destination Kinesis stream again and perform a custom thresholding logic. So we compare the aggregated data to the threshold stored in DynamoDB and send an alert if necessary using SNS. And the other thing you see in this diagram is the error stream. So every time you process a stream of data in Kinesis Analytics, there could be some error, and Kinesis Analytics delivers those data to a destination. In this case, it is a Firehose delivery stream and store a copy of that data. Here in this case, it is an S3 bucket. So let's take a closer look at the middle part where Kinesis triggers Lambda and discuss a few best practices here. One of the important aspects you have to remember is that Kinesis scales in terms of shards. So each shard in a Kinesis stream has a certain capacity, 1 megabyte per second in and 2 megabyte per second out. So this is your unit of scale when you configure a Kinesis stream. So one important thing to remember is that each shard that you have in your Kinesis stream, you get one parallel concurrent invocation of Lambda. The other thing is you have a parameter called batch size, and this configures how many messages max Kinesis stream will send to one Lambda function invocation. The default size is 100 and max is 10,000. Sometimes you may find that the amount of processing that you want to do in your Lambda function is so much that you can't keep up with the messages flowing in. So in that case, you may want to consider implementing a so-called fan-out pattern. And in this pattern, you take your Lambda function logic and split it into two parts. So the first part is the dispatcher, and this is responsible for getting this big pile, this big part of messages from a Kinesis stream, and making smaller batches out of that, and invoking a Lambda processor function for each of those batches in parallel. So you can get a higher throughput and lower latency, but you lose the strict message ordering. So this works for some use cases, but obviously not for all use cases. Some best practices. Remember, you have to tune the batch size, and this lets you invoke less Lambda functions, so you pay less because you are charged by the amount of Lambda invocations. Also, please tune your memory settings for your Lambda function. If you tune the memory settings higher, you get more CPU, and that might help you processing the invocations faster. if you have control over the client-side processing of your pipeline, so this means the producer part, I would highly recommend taking a look at KPL, the so-called Kinesis Producer Library. And this is a client-side library and locally batches multiple Kinesis messages into one Kinesis record. And it also uses a protocol buffer to reduce the message size. And this lets you fully saturate your Kinesis stream capacity. So, in summary, we took a closer look of how to use DevOps tools to automate your serverless deployments, and we discussed 3 different patterns, so the web application, a data lake, and stream processing. And I highly encourage you to take these patterns home with you and see what fits in terms of solving your business problems. And also, please let us know what you can build with serverless. We're always interested in new ideas and new patterns. And here are some white papers which will tell you more about serverless patterns and some of the considerations. So thank you very much and enjoy the rest of the conference.